In this video lesson, we are going to look at Euclidean geometry. And more specific, we're going to look at Gr11 theorems as an overall of all the theorems. And just before we start, a reminder on how we do mathematics. Now make sure that you understand all the steps of the examples, and then also when you see the pause button, make sure to pause the video and do the question on your own before continuing, and then to mark it. Make sure that you understand if you make any mistakes, where you make your mistakes. Alright, now an overview. We're going to look at the theorems, specifically the theory behind it, and also the reasons that you use or give when you use the theorem in a question. And then we're going to apply the theorems, and this is going to be quite simple questions where it only focuses on the theorem itself. And then we're going to look at more complicated questions which comes out previous exam papers. So for theorem 1, we have a circle, and then the center of the circle is O. Then we draw a chord on the circle anywhere, and the chord is BC, and then from the center of the circle we draw a line to the chord with the condition that that line is 90 degrees with the chord, so perpendicular on the chord. Now if we do that, then it will divide the chord in half. Alright, so theorem 1 says that a line drawn from the center of a circle perpendicular to a chord bisects the chord. And when you use this, so let's say that the question says that the chord is perpendicular to the line, and you want to say, okay, that means that BA is equal to AC, then the reason is line from center is perpendicular to chord. Now the converse of theorem 1 is just the other way around. So we still have our circle with center O and our chord BC. Now we draw a line from the center, but now we know that it divides the chord in half. That's what's given to us. So from that we can deduce that if that line divides the chord in half, therefore the line is perpendicular to the chord. So the theorem says that a line drawn from the center of a circle to the midpoint of a chord will be perpendicular to the chord. And our reason is line from center to midpoint of chord. And for theorem 2, we have a circle and with a chord BC. Now we draw a line on that chord with two conditions. So the line is both perpendicular to the chord and it divides it in half. Right? So from that we can say, if that is true, then that line must go through the center of the circle. So theorem 2 states that the perpendicular bisector of a chord passes through the center of the circle, and our reason is perpendicular bisector of chord. Moving on to theorem 3, we have our circle and with center O. So now we are going to from BC, it can be the arc or a chord BC, and subtend an angle to the center of the circle. Then we subtend another angle, but now to the circumference of the circle, right? But from the same chord BC. So what happens if we do that is the angle that is formed at the center of the circle will be twice as big as the angle at the circumference anywhere else on the circle. And the theorem says that the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at any point on the circumference of the circle. And our reason is angle at center is 2 times angle at circumference. Now corollaries, basically things that follow on this, or what will be true, is let's say our circle, the angle at the center is now 180 degrees, meaning it's actually now a straight line which forms the diameter of the circle. If that is going to happen, obviously if it halves, then it's going to be 90 degrees, which makes it a right angle. So we can then say that the diameter subtends a right angle at the circumference of the circle. And then also the other way around, if the angle at the circumference of a circle is a right angle, then we can say that it is subtended by the diameter. And our reason is angle in semicircle. Now for theorem 4, we have our circle, and from arc or chord CD, we subtend an angle to the circumference of the circle at B. Then we subtend another angle anywhere else on the circle, say at A, and what then happens is that if it is subtended by the same chord or arc, those two angles will be equal to each other. So the theorem says that the angles on a circle subtended by a chord of a circle on the same side of the chord are equal. And our reason is angles in same segment. So the corollaries that follow on that is, let's say that we have a chord, so equal chords subtend equal angles at the circumference of the circle. So let's say we have chord CD and then any other chord EF. So the angles subtended by those two, and if they are equal, the angles subtended by those two chords will also be equal. And then the reason equal chords subtend equal angles. Right, then for the converse of theorem 4, meaning we're just going to go the other way around. So basically, let's say we have a quadrilateral ABCD. We have this chord CD and it subtends to B and to A. Now, if those two are given to be equal, if those two angles are given to be equal, then we can say that therefore this is a cyclic quadrilateral, meaning it lies in a circle. So it says if two angles subtended by the same line are equal, then ABCD is a cyclic quadrilateral, and our reason will be angles in same segment. Then for theorem 5, we have a circle, and then inside the circle we have a quadrilateral ABCD, and if it is a cyclic quadrilateral, then it means that the opposite angles are supplementary, or in other words, they add up to 180. So C plus B adds up to 180, and A plus D also adds up to 180. So the theorem states that the opposite angles of a cyclic quadrilateral are supplementary, and our reason is opposite angles of cyclic quad. Now the corollaries is that if the line, any line is extended, since we know that the opposite angles add up to 180, and we also know that angles on a straight line adds up to 180, this follows that the angle at C that is subtended, that angle over there, should then therefore be equal to the opposite interior angle B. And this theorem states that the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. And our reason is exterior angle of a cyclic quad. Then the converse of theorem 5. So here we only have a quadrilateral. We don't know whether it's cyclic or not, but if it is given that C plus B is 180, so the opposite angles are either one pair of the opposite angles are supplementary, and if one pair is supplementary, then obviously the other pair will also be supplementary, because quadrilaterals always add up to 360. So, but if you only know that one of them, at least one of them, adds up to 180, then you can say therefore this must be a cyclic quadrilateral. And this is the other proof with the previous one, where we had a cyclic quadrilateral subtended by the same arc. These are the two reasons that you use to prove that a quadrilateral is in fact a cyclic quadrilateral. So it says that a quadrilateral is a cyclic quadrilateral if the opposite angles are supplementary. And our reason, opposite angles of quad supplementary. Now for theorem 6, our circle, and then we have a point outside the circle at C. Now if we draw two tangents from that point, and where those two tangents touch the circle is at A and B respectively, then if the tangents are drawn from the same point outside the circle, then these two tangents will be equal, meaning from A to C and from B to C, both of these will be equal. So the theorem says that two tangents drawn to a circle from the same point outside the circle are equal in length. So the reason is tangents from the same point. Then for theorem 7, once again we have our circle, and then we also draw a tangent to the circle at A. Now at that point A, we also draw a chord AB, and then that forms an angle between the chord and the tangent forms an angle, all right? And then if we subtend an angle out of the chord AB, that also forms an angle at C, at the circumference of the circle. So the tangent theorem says, or theorem 7 says, that those two angles will be equal to each other. So we can do it from the other side as well. We can draw a chord AC, and then that forms an angle between the tangent and the chord. And then if we subtend an angle to B, that angle will be equal to the angle formed between the tangent and the chord. So it says that the angle between the tangent to the circle and the chord drawn from the same point of contact is equal to the angle subtended by the chord in the alternate segment. And your reason is simply the tan-chord theorem. Now let's look at a summary of all the theorems that we did. And this is going to form a type of a mind map, because you need to know all the reasons off by heart. So I'm going to do the summary, and then I'll just explain how do you use it. So first of all, we have theorem 1 and 2, and it said that if you draw a line from the center of the circle perpendicular to a chord, then that line must divide the chord in two. And then the line from the center to the midpoint of the chord. So basically, if you draw a line from the center of the circle and that divides the chord into two, then that must be perpendicular to the chord. And then finally, the perpendicular bisector of a chord means that if you draw any line, it's both perpendicular and divides the line in two, then it must go through the center of the circle. Then we had theorem 3. And theorem 3 is where the angle at the center is 2 times the angle of the at the circumference, subtended from the same chord, of course. And the corollary was that the angles in semicircles, so if it is the diameter, or an angle subtended from the diameter, is always equal to 90 degrees. Then we have theorem 4. So theorem 4 is angles in the same segment are equal, all right? And then also equal chords subtend equal angles. So if you have two different chords but they are equal, then the angles that they subtend will be equal as well. Then for theorem 5, the opposite angles of a cyclic quad, they add up to 180, all right? And then also that the exterior angle of a cyclic quad is equal to the opposite interior angle of a cyclic quad. And then opposite angles of quad is supplementary. That's if you only have a quadrilateral and you need to prove it that it is a cyclic quad. All right, and then for theorem 6 is basically that the tangents from the same point, which means if you have two tangents that are coming from the same point outside of a circle, those two will be equal in length. And then the final theorem, theorem 7, which is the tan-chord theorem, basically says that the angle between the tangent and the chord is equal to the angle that is subtended by that same chord. Now, this summary, you can make your own, and I would actually advise you to make your own summaries, because that actually helps you to remember it better. But then when you do the questions, keep the summary at hand, all right? While you're practicing, so that if you are looking for things that are equal or looking to solve a problem, you can quickly revise, like just do a quick recap on what the sketches look like, and then see if you can find similar patterns in your question that looks like the summaries. Now, this specific summary you can also download from the website. It should be at the bottom of the homepage under student resources. You can find it there if you want to, and then also a summary that is a bit more in detail with all the official theorems as well. Okay, so this was the theorems. Now let's look at applying the theorems. Okay, so for the first one, it says that in the circle with center O, LO is 26 centimeters, OP is 10 centimeters, and OP is perpendicular to MN. Calculate the length of MN. Now, with Euclidean geometry, normally we take a pencil and just study the diagram and make notes of everything that they've given us, see what angles we can solve for, what can we see, can we use? And then basically first we kind of solve the whole thing with a pencil before we go over and then put everything on paper in the structure that is required. Okay, now when you do this, keep your summaries by hand, close by, especially in the beginning when you're starting to like learn the theorems, when you don't know them off by heart yet. So first of all, we look at our diagram and then we see which theorem kind of relates to the one we have to solve at the moment. And we can see that this one definitely looks like theorem 1 or 2, right? And we are given that OP is from the center of circle and is perpendicular to MN. So what we can use from theorem 1 is that this line OP will then bisect MN, all right? And MN is the line that we need to solve for. And therefore, if we know that, then we can basically solve for MP, because if we have MP, we know that MN is just double MP. Now, to solve for MP, we can focus on this triangle, which is actually a right angle triangle. And if we have OM, that length, we can use Pythagoras to solve for MP. All right. Now, something that is that we can easily miss, like if you're not thinking about it, is that the radius is everywhere. The radius on the circle is everywhere the same. Okay, and especially if you have like a more complicated diagram, you don't always like think of that. It's something that we easily kind of miss. So in this case, we know that OM is also 26 because it's the radius of the circle, which is also OL. Okay, and that is how we're going to solve for MN. We are going to start, so we can now start and we can say, okay, we said that OM is equal to 26, and the reason is radii, okay, because the two radii. Then we can say that we can solve for MP. Okay, now with Pythagoras, remember that this is the hypotenuse. So with Pythagoras, we take the hypotenuse and we add the two smaller sides, but now we want the smaller side. So I'm going to say that MP squared is equal to my longer side, the hypotenuse. So that's going to be 26 squared minus the other short side, 10 squared. And the reason is simply Pythagoras. Okay, so now to solve for MP, I'm just going to take the square root on both sides. So 26 squared minus 10 squared, and then we can put that onto the calculator. Square root of 26 squared minus 10 squared, and this is then equal to 24. Okay, now for the final thing, we can state that MP is equal to Pn, and our reason is going to be line from center is perpendicular to chord. So line from center is perpendicular to chord. Okay, therefore we can say that Mn will be double MP, so that's going to be 48. And this is our final answer, and they have given us units, so I'm going to put my final answer as 48 centimeters. So this is one for you to do. It says, in circle with center O, the radius is 10 centimeters, and the chord PR is 8. So PR is 8, we can just make that in pencil. And then calculate OQ correct to 1 decimal place. So OQ is this one from the center of the circle. Now, what do we know? So from our summaries, I know that this is the line from the center which is perpendicular to the chord, which means if it's perpendicular, then it's going to bisect that chord. So that means QR is 4. And then we know that that is the radius, but OR, if we draw a line here, OR is also the radius, so that's also going to be 10. And then we can use Pythagoras to find the third side. Okay, so we are going to start and say that we can start with OR. We can just state that OR is 10 because of the radii. Okay, and then we can say, okay, but PR is 8. That was basically given. Okay, and therefore, and then we know that PQ is QR, so PQ is QR, and our reason is line from center is perpendicular to chord. Okay, therefore we know that QR is equal to 4. Okay, and then we can go ahead and solve for OQ. OQ squared is, now OQ is the shorter side, so we're going to take the hypotenuse 10 squared and minus the other short side 4 squared, and then OQ is the square root, so we can so long say, okay, we know this is 100 and that is 16, and then we can put that into the calculator. Oh, and we have to state our reason. Our reason here was Pythagoras when you set up that relationship. So we've got the square root of 100 minus 16, and that gives us 2 square root 21. Now also they haven't specified, oh, they said correct to 1 decimal place. So then we're just going to put that to decimal places, and this becomes 9,2. Okay, now this one, if we look at our summary, we can see that it looks like Theorem 3. And Theorem 3 says that the angle at the center is 2 times the angle at the circumference. So meaning we can say A is then twice 32 and give our reason. Angle at center is 2 times angle at circumference. So A is equal to 64 and angle at center is 2 times angle at circumference. Now in this case, we have that C, so subtended from BC, we have a C at the angle at the center, and then from the same chord we have the angle subtended to the circumference of the circle, which is 48. So this is again just going to be Theorem 3, and we can use the same reason there. So we're going to say that C is equal to twice 48, so 50 times 2 is 100 minus 4 is 96 degrees, and the angle at the center is 2 times the angle at the circumference. Right, now in this case, if we look at our summary, this is the diameter, okay, and we know that the diameter subtends a 90-degree angle, okay. So then we have a triangle over here, and we can apply angles of a triangle to solve for D, because they add up to 180. Okay, and our reason is going to be angle in semicircle. So I have that BAC is equal to 90 degrees because of angle in semicircle. And then I can say that all of these angles add up to 180. So D plus 90 degrees plus 40 degrees adds up to 180 degrees. And the reason is angles of a triangle. And then just solve for D. So D is equal to 180 minus 90 minus 40. So that's going to be 90 minus 40, which is 50 degrees. Okay, now if we look at our summaries, we can see this looks like Theorem 4. And we have CD that subtends A, that angle, and CD also subtends B. So this is going to be angles in the same segment, whereas they are equal. And then from the other side as well, AB subtends A and the 31-degree angle, so they are equal. So I'm basically just going to say A is equal to 31 degrees, and my reason is simply angles in same segment. And then also B is equal to 42 degrees, also angles in same segment. Okay, now for this one, we have basically the same as we saw earlier, that we have these two angles that are in the same segment. Both of them are subtended by the chord CD, but we do not know what this angle is. However, we do have that these two lines run parallel to each other. So we can think about things like co-interior, alternate, corresponding angles. Now this D and C, they form a Z or an N, and that is alternate angles. And we know that alternate angles are equal when the lines are parallel. So we can use that. So first I'm going to say that C is 24. And my reason is angles in the same segment. Right? And then I can say that D is also 24 because of the alternate angles. And I have to say which lines are parallel. So BC is parallel to AD. Now for this one, we can see that it looks like theorem 5, and we know that the opposite angles of a cyclic quad, they add up to 180. So to find A, I can say that A plus 72 adds up to 180. So that's my relationship, and then basically solve for A, and then do the same for B. So A plus 72 degrees is equal to 180 degrees. Angles, the reason is opposite angles of a cyclic quad. Okay, and then solve for A. A is equal to 180 minus 72, so that's going to be 108 degrees. And then similarly we can do B. B plus 130 degrees is equal to 180 degrees because of opposite angles of a cyclic quad. And then B must be equal to 180 minus 130, so that's going to be 50 degrees. Now looking at the summary, we can see this is definitely theorem 5, and we know that the exterior angle of a cyclic quad is equal to the opposite interior angle. So E is simply going to be equal to 110. So E is equal to 110 degrees, and our reason is exterior angle of cyclic quad. Now similarly we have this one also applying to theorem 5. We've got K, L and M to solve for. So K we know is equal to 55 because that's the exterior angle of the cyclic quad, and it's equal to K, opposite interior angle. Also we are given that these lines are parallel, so think about your three things: the co-interior, alternate and corresponding angles. Now we can see that K and L are co-interior angles, so they add up to 180, so that's how I'm going to solve for L. Then for M, there's one of two things I can do. I can say that the opposite angles of a cyclic quad adds up to 180, or easier, that does not require any calculations, is to say that M is equal to 55. They form a Z, so these two angles are alternate angles, so I'm rather going to use that. Alright, so first of all we can say that K is equal to 55 degrees, and our reason exterior angle of a cyclic quad Then moving on, we can say that L plus the 55 degrees is 180 degrees because they are co-interior angles, and our lines are AB is parallel to DC, and solve for L. So L is 180 minus 55, so 180 minus 50 gives us 130, minus another 5 is 125 degrees. And then finally, we can just say that M is equal to 55 degrees because of alternate angles, and the lines are AB is parallel to DC. Now for this one, if we look at our summary, okay, so this point, this AD is a tangent as well as CD, so that means that the line AD will be equal to CD, right? And our reason is tangents from the same point. Then, knowing that, we can see this is an isosceles triangle, and we know in isosceles triangles when the two sides are equal, the two angles are also equal. Right, so this is also going to be 62 degrees. Now, with angles in a triangle, we can solve for P because they add up to 180 degrees. And then we can, to find Q, that's quite easy, or well, simple, if we can recognize that it is the tan chord theorem, because this angle is the angle between the tangent and this chord, and this chord subtends this angle over here. So they are both equal to each other, and our reason is tan chord theorem. Now, to start off and writing everything down, we can say that AD is equal to CD, and our reason is tangents from the same point. So tangents from same point. Okay, then we can say that CAD, so CAD is equal to 62 degrees, and that is just equal sides, equal angles. And then to find P, we're going to say P plus 62 degrees plus 62 degrees is equal to 180 degrees, and this is angles of a triangle. And then just solve for P. So P is 180 minus 120 minus 4. If you just take the 62 both to the other side, or you can just do it on your calculator. But that's going to be 60 minus another 4, so that's 56 degrees. All right. Then going over to Q, we saw Q must be equal to 62 simply because of the tan chord theorem. All right. Now for this one, if we look at our summaries, we can see that this also has a point outside of the circle, and this tangent AC is therefore the same as BC because they are both subtended, or the tangents are from the same point. So this is also 50. Okay. Now another thing that is not in the official theorems is that the radius and the tangent at the same point are perpendicular to each other. Okay. So basically, this will form a right-angled triangle where we can apply Pythagoras' theorem and solve for L. Okay, so I'm going to say that BC is equal to 15, and my reason is tangents from the same point. Okay, then I'm going to say that OBC is 90 degrees because the radius is perpendicular to the tangent. Okay. Then I can say that L squared, this is now the hypotenuse side, so L squared is equal to 8 squared plus 15 squared. And my reason is Pythagoras. So to solve for L, L is the square root of 8 squared plus 15 squared. And then I can just type that into the calculator, and I'll have 8 squared plus 15 squared is equal to 17. And then we're done. Okay, now on this one, we can see that the tan chord theorem is going to be applicable because we've got this angle which forms between the tangent and the chord, and that is equal to the angle subtended by the chord. Same with the 40 degree and B. And then C, we've got one of two choices, either angles of a triangle or angles on a straight line. Okay, so A is equal to 72 degrees, and our reason is tan chord theorem. And then we have that B is equal to 40 degrees, also tan chord theorem. Okay, and then C, I'm going to use angles on a straight line. So C plus 72 degrees plus 40 degrees is equal to 180 degrees. Angles on a straight line. And then solve for C. So taking the other two and subtracting them, we've got 180 minus 72 minus 40 is equal to 68. We just go back there. So this is 68 degrees. Now, in this case, D and E, so again, the tan chord theorem applies here. And then for E, we're going to use theorem 3, where we see this is the diameter, and this means this is an angle in a semicircle, so E is then equal to 90 degrees. So simply say D is equal to 30 degrees because of the tan chord theorem. And then E is equal to 90 degrees because of angle in semicircle. Right, and then this one. Again, we can apply the tan chord theorem and say that G is equal to 36. We can also, because you see this VZ subtends G, then also this VZ also subtends H, so we can also use the tan chord theorem there, or we can actually use theorem 4, which says angles in the same segment. So after you found G, you can basically say, but G and H is equal because of angles in the same segment. And then to find I, there's one of two ways. You can say that this is the diameter, and say that means that it subtends a 90-degree angle. Or I think easier, okay, and then use angles of a triangle. Or easier, we know that the radius is perpendicular to the tangent, which makes this I plus 36 equal to 90 degrees. And therefore we can solve for I. Right, so let's start and say that G is equal to 36 degrees, and this is the tan chord theorem. And then we can say that H is also equal to 36 degrees. So I'm going to use the reason angles in the same segment. Okay. And then I'm going to say that I plus 36 is 90. So I plus 36 degrees is equal to 90 degrees. And this is because the radius is perpendicular to the tangent. And then solve for I. I is then 90 minus, let's say 90 minus 40. That gives us 50, and then that's 54 degrees. Okay, so that was the easy questions. Now let's look at some exam type questions. So for question 1, in the diagram below, PT is the diameter of the circle with center O. M and S are points on the circle on either side of PT. MP, MT, MS and OS are drawn. So M2 is 37 degrees. Calculate with reasons the size of M1. So 1.1 is M1. Now let's look at our summary, and when we look at the angle that is subtended at M, that is subtended from the diameter. So that's going to be angles in a semicircle. So they form a 90 degree angle there. So then we can get M1 when we add these two and equate them to 90 degrees. Okay, so let's do that. So this is 1.1. Therefore, I can say that angle M1 plus angle or plus 37 degrees is equal to 90 degrees because of angle in semicircle. Okay, and then just to solve for M1, we take the 37 to the other side and we subtract. So that is going to be 90 minus 37. And that's equal to 53 degrees. Okay, now for 1.2, for O1, So O1 is subtended by PS, and that is subtended to the center of the circle. And then we've got the same, also M1 subtended to the circumference. Now we know that the angle at the center is twice the angle at the circumference, so we can say O1 is then equal to twice M1. So this is going to be equal to 106 degrees, where we have that the angle at center is equal to 2 times the angle at circumference. So for question 2, in the figure below, AB and CD are chords of the circle with center O. OE is perpendicular to AB, and then CF is equal to FD. OE is 4 centimeters, and OF is 3 centimeters. Then CD is 8 centimeters. So this all is 8 centimeters. Okay, now comparing this diagram to our summaries, we can see that it's definitely going to be Theorem 1 and 2. And for the first part, where we have that the line from the center of the circle is perpendicular to the chord, we know that it's going to bisect that chord. So that is basically Theorem 1, line from center to perpendicular to chord. And then also from here, we've got the line from the center that bisects the chord. So that's Theorem 2, and therefore we know that this is a 90-degree angle. Okay. And in question 2.1, it says calculate the length of OD. Now, OD is the radius over here. So to calculate that length, we can say that because this is 4, it's given that CF is equal to FD. Okay, we can use Pythagoras to calculate OD. So let's start with 2.1. And just to write down everything that's important for solving OD only. Now, first of all, we know that CD is equal to 8. That is given. And then we know that FD is, so therefore FD is equal to 4 because CF is equal to FD. Okay. So now we have that, but before we can actually use Pythagoras, we just also need to state that this is a right angle triangle, because that wasn't given. This is through the theorem. So first of all, we need to say that OF is perpendicular to FD, okay, and that comes from Theorem 1, line from center, or actually Theorem 2, the converse of Theorem 1, the line through center and midpoint. So not converse, let's just say line through center, line through center and midpoint. Okay, and therefore OF D is equal to 90 degrees. Okay, now we can use Pythagoras. So now to find OD, we say OD squared, which is the hypotenuse side, is the other two added together, 3 squared plus 4 squared, and our reason is Pythagoras. So therefore OD is the square root of 3 squared plus 4 squared. Okay, now if we simplify that, this is going to be 9 plus 16, which gives us 25. So it's the square root of 25, and that's just equal to 5. Okay, and that's our final answer for 2.1, and our units are given in centimeters. Then for 2.2, we have to calculate the length of AB. Now, how to do that? If we have EB, we can just double that. And to solve EB, we can use this as a right angle triangle. And we also know that OD is the radius and OB is also the radius. So they must be equal to each other. So if this is 5, then this must also be 5. And then just use Pythagoras to find EB. Okay, so I'm going to start off and say that OB is equal to 5 because of the radii. Then I'm going to say that EB, so solve for EB using Pythagoras. So EB squared is then, so now it's the shorter side that I'm trying to find. So I'm going to say 5 squared, the hypotenuse, minus the other short side, 4 squared. So this is Pythagoras, and then just solve for EB. So that's the square root, and this is 25 minus 16. And 25 minus 16 is 9, and that gives us 3. Okay, so this is 3. Then we can say that AE is equal to EB, and our reason is line from center is perpendicular to chord. Right? And therefore AB is equal to 6 centimeters. Question 3. In the diagram, M is the center of the circle passing through the points L, N, P. Then M or PM is produced to K. KL MN is a cyclic quadrilateral in the larger circle, having KL equal to MN. Okay, so that is also given on the diagram. L pair is joined, and KML is 20. So this is this KML is 20 degrees, that angle over there. So for 1, write down with a reason the size of NKM. Okay, so the reason we are going to use there obviously is equal chords subtend equal angles, because we can see that this chord over here is subtended, or this angle is subtended by that chord, but we know that this chord is equal to that chord, and therefore this angle is also equal to 20 degrees. Okay, so we know that K or NKM is equal to 20 degrees. So our reason is that the equal chords subtend equal angles. Okay, now for 2, this was 1, then for 2, give a reason why KN is parallel to LM. So look for angles like your alternate angles or corresponding angles or co-interior angles. Now we see that these two both are 20, and that if KN, with KN and LM, it forms a Z. And if they are equal, it means that KN and LM are parallel. Okay, so therefore our reason is simply going to be that the alternate angles are equal. So alternate angles are equal. Then for 3, prove that KL is LM. Okay, so we need to say KL is LM. Now, when we look, this M is basically the center of the circle, and ML is the radius of the circle, so as well as MN is also the radius of the circle, so they are equal to each other, right? But we are given that KL is also equal to MN. And therefore, if both KL and LM is equal to MN, it means that they must be equal to each other. Okay, so to write that down, I'm going to start and say that LM is equal to MN, and that is the radii. But we also know that KL is equal to MN because it was given. And therefore, if both LM is equal to MN and KL equal to MN, therefore KL is equal to LM. So next we've got 4, or let's say 4.1. Calculate with reasons the size of K in M. Now K in M lies over here, so this is the N1. Now we know this is a cyclic quad, so one of the things we can think about is that the opposite angles are equal to 180 together, or supplementary. The other thing we need to keep in mind is that these two lines are parallel, so maybe if we had this angle, we can add up these two to 180. So which will be easier to get? To find that angle, basically we know now that this is a isosceles triangle, which means that this angle is also 20. Okay, so there we have it. So if we have these two angles, we can find the third angle of the triangle, and then we can basically use the fact that these two are supplementary and solve for k in M. Okay, so let's start and say that K2 is also equal to 20, and that is because of equal sides equal angles, right? Then we can say that L2, angle L2 plus 20 is equal to 180 degrees because of angles of a triangle. They add up to 180, and then to solve for L2, we just take the 20s to the other side. So L2 will be 140 degrees. Now we can say that L2, or actually not L2, we've got the value. We can say that K in M plus 140 degrees is equal to 180, and that is the opposite angles of a cyclic quad. Let's just write it here, quad. Okay, so that makes for K in M to be equal to 40 degrees. Okay, now for 4.2, LPN. So LPN. Now, as we previously stated, this angle over here, these are co-interior angles. Okay, so now that we have this K in M, we can actually find that. And why do we want this angle? If we look at the smaller circle, then we see that LN subtends to the center of the circle and forms this angle over here. And then that same LN subtends to the circumference of the circle and forms this angle that we are looking for. Okay, and this is the theorem that states that the angle at the center is twice the angle at the circumference. So let's start off by finding LMN. So we can say that LMN will be, or LMN plus the angle KNM, or K or N1 for that matter, so plus 40 is equal to 180, because they are co-interior angles, whereas we saw, or given, or well, we had to give a reason why KN is parallel to LM. Okay, then we can say, okay, LMN is therefore 140 degrees, right? And then we can just state, okay, if this is 140 degrees, then the angle at this the circumference must be half of that. So LPN should be equal to 70 degrees, and the reason is angle at center is 2 times angle at circumference. Now for question 4, in the diagram below, DCO is 25 degrees and O is the center of the circle. A, B, E, C, and D are points on the circumference. Calculate giving reasons the sizes of number 1, D1. Right, so knowing this is the center of the circle, we know that where are our radiuses? So this is a radius, that's a radius, that's a radius, meaning that in this triangle, we've got an isosceles triangle, which means that this angle is equal to this angle, and that is D1. So I'm going to say that OD is equal to OC, and the reason is radii, and therefore we can say that D1 is also equal to 25 degrees because of equal sides, equal angles. Right. Now 2 for O1. So O1 here, if we look at the triangle ODC, O1 is the exterior angle of this triangle, and we know that the exterior angle of a triangle adds up to the opposite interior angles. So O1 is 25 degrees plus 25 degrees, and our reason is exterior angle of triangle, and then we've got O1 is equal to 50 degrees. Then for number 3. Now we're looking for A1. So A1 is this angle, and both A1 and D1 are both subtended by BC. So they are equal because they are angles in the same segment. So A1 is also equal to 25 angles in same segment. Right. Now for the final one, for E. So if we look at E, we can see E forms part of a cyclic quadrilateral. It actually forms part of two cyclic quadrilaterals, so you can choose which one you want to use. But we do know that the opposite angles of cyclic quadrilaterals add up to 180. So meaning A1 and angle E, they add up to 180 because they fall in a cyclic quadrilateral. So I'm going to say that E plus 25 degrees must add up to 180 degrees, and these are opposite angles of cyclic quad. And then just solve for E. So E is then 180 minus 25, so this is going to be 155 degrees. Okay, now for question 5. A, B, C, and D are points on the circumference of the circle in the diagram below. ECF is a tangent at C, so this line is the tangent at C. B1 is B2, so these two angles are equal. 1. If B1 is X, find with reasons two other angles equal to X. So we have B1 is X. Now there's three other angles, so I'll just state all three of them. Now, first of all, B1 is equal to B2, so that means that B2 is also equal to X, all right? Then, whenever you see a tangent, when you look at the summaries, first thing, obviously, think about tangent theorem. So let's see if that applies. We've got this triangle over here, and this angle, that means that this angle between the tangent and the chord is equal to the angle that is subtended by that chord. So this C1 is also equal to X because of the tangent theorem. And then we can see that B1 and C2 are both subtended by AD. So they are angles in the same segment, making them equal to each other. Yeah, so those are all equal to X. Now, to write that down, we can say that angle B2 is equal to X. That is given. Then we can go and, okay, this one. Then we can go and say, okay, but C1 is also equal to X because of the tan chord theorem. And then we can say that C2 is equal to X, and they are angles in the same segment. Right. Now, moving on, we've got question 2. Hence, show that DC bisects ACF. So basically, we already shown that these two are equal. We can just state that, because then we can just conclude that this DC bisects or cuts in half this ACF. So I'm just going to state that angle C1 is equal to angle C2 is equal to X, and this was proven above. I'm saying proven above because we're now in a new question. So when you use something that you've shown in the previous question, you just write proven above. And then we can say, therefore, DC bisects angle ACF. Done. Question 6. In the figure, ABCD is a cyclic quadrilateral. So ABCD. AB is parallel to DC. AB is parallel to DC in circle with center O. BC and AD produced meet at M, and then D3 is X. So D3 is X. Now for question 1, show that MC is equal to MD. MC is equal to MD. So if in a triangle in this, and if it's two lines in the or sides in the same triangle, then the first thing I always think of is if I can solve, or if I can prove these two angles equal to each other, then I can state that the sides must be equal angles, equal sides. Now how can I actually show that this is also x? Now let's look at what else we have. We've got a cyclic quad, and if we look at our summaries, we can see that theorem 5 states that the angle at the exterior angle of a cyclic quad, and this is the exterior angle, so that angle must be equal to this angle over here. Okay, and we also see that these lines are parallel, meaning that the corresponding angles will also be equal. So C2 will also be equal to x because they are corresponding angles and they are equal. Okay, so there we have it. There we've shown that both of these angles are x, therefore both of these sides will be equal. So to write that down, we're going to say that angle B is equal to x because of the exterior angle of cyclic quad. And then we can say that angle C2 is equal to x because they are corresponding angles, whereas AB is parallel to DC. And therefore C2, or let's say D3 is equal to C2. Okay, and therefore we can say that MC is equal to MD, equal angles, equal sides. So notice that I have now shown that the sides are equal because of the angles are equal. So the reason will be, I'm first stating because of equal angles we end up with equal sides. Right, so for number 2, if D3 is x, determine the value of M in terms of x. So this is quite easy because we've got the other two angles in terms of x, and we know that angles of a triangle add up to 180. So I'm just going to say that x plus the angle M adds up to 180 angles of a triangle, and then just solve for M. So this is going to be 180 degrees minus 2x, and that's done. Then for 3, hence show that BODM is a cyclic quad. So BODM, that one there. So 2 ways to show a cyclic quad is to show that the exterior angle is equal to the opposite interior angle, and we can see that we've got an exterior angle over here, so but we don't have that angle. The other way is to show that the opposite angles add up to 180. Okay, so this actually leaves us with what I think is going to be the easiest, because we just found M in terms of x. Let's see if we can find O1 in terms of x, and then if we add these two up, will it give us 180? Then, because if it does, then we've proven it, and obviously show that it is a cyclic quad, meaning the chances are good it's going to add up to 180. Okay, so how can we find O1? O1 subtended from DB, but DB also subtends A. Now that means that O1 is twice as big as A, and A and D3 are corresponding angles. So I'm going to say that A is x, okay, because they are equal, but O1 is twice x because that's subtended. So then I've got 2x there, and I know that M is 180 minus 2x, and then if we add those two, we should get 180. Okay, now let's start. We saw that A is equal to x, so that's corresponding angles, and AB is parallel to DC. Then we can say that O1 is equal to 2x because the angle at the center is twice the angle at the circumference, right? Now let's add up. So now we're going to say that m, let's start with 01 plus m is equal to 2x plus 180 minus 2x. Okay, so that adds up, because the 2x and the 2x cancels, that ends up with 180 degrees. So therefore I can say that the quadrilateral is BODM is a cyclic quadrilateral. And my reason is going to be the opposite angles of the quad is supplementary. So actually that should actually come next here, but opposite angles of quad is supplementary. Okay, so that actually comes in there. Right, then that is done for question 6. And now for question 7. So O is the center of the bigger circle O. O lies on the circumference of the smaller circle. OWVU are points on the circumference of the smaller circle. TSVU are points on the circumference of the bigger circle. So for 1, name 4 other angles equal to x with reason. So what x's do we have? We've got that O1 is 2x. And from our summary, we can see this theorem 3, where O1 is subtended to the center, and then from TU also subtended to the circumference. So meaning that O1 is twice S1, so that's going to be x. Then also we can see the same, that TU subtends also V3, so that's also going to be equal to x because it's angles in the same segment, where we see theorem 4. And if we look at the smaller circle, we've got this angle is subtended by OU, but this OU also subtends W1. So this is also going to be equal to x. And then lastly, which is not as obvious, we've got the center as O. So let's see, this OV is the radius, but OU is also the radius, meaning that this is an isosceles triangle, which means that this angle and this angle are equal to each other, making this also x. Okay, equal sides, equal angles. So let's write that down. So we can say that S1 is equal to x, so angle at center is 2 times the angle at the circumference. Okay, then we can say that V3 is equal to x, angles in the same segment. Okay, then we can also say that W1 is x, also angles in the same segment. That just that just happens now in the smaller circle instead of the bigger circle. And then finally we can say that OV is equal to OU, and that is the radii. And therefore we know that OUV is equal to x, where we have equal sides, equal angles. Okay, that was number 1. Now for number 2, determine the size of W2 in terms of x with reasons. Okay, so let's look at what else can we see should be equal to W2 is it's subtended by UV. Any other angles? We got UV also subtending O2, so they must be equal to each other. And O2 is easy to find because that's it just forms angles on a straight line with 2x. So to start off, I'm going to say that O2 plus 2x is equal to 180 angles on a straight line. And then I can solve for O2. O2 is equal to 180 minus 2x. Now we know that W2 is equal to O2, so that's also equal to 180 minus 2x. And our reason is angles in the same segment. Okay, and there we have it. That is our answer there. So to do number 3, prove WS is equal to WV. So to do that, I'm just going to clear the page, start a clean page. So this is 3. And just as a reminder, we saw that this is x, this is x, this is 180 minus 2x, and then we know that this is x. Okay, what else was x? This was x. So if we want to prove two sides equal and they fall in the same triangle, then first thought, prove the two angles equal. Now let's see if we can play around and find S2 and V1 both in terms of x, because if we do that and we see that, okay, they are equal in terms of x, then we can say that equal angles, equal sides. Now let's try and find, okay, this is the diameter, right? And this angle over here is therefore a 90-degree angle because of this angle in semicircle. Now we can find S2 in terms of x because we have that side of the angle. So I'm going to say that TSV, or let's start with saying that x plus S2 is equal to 90 degree because they are angle in semicircle. Okay, and to solve for S2 we have 90 degrees minus x. Okay, now moving on, we want to find the other angle in terms of x. So we can find W3 in terms of x, and then with angles of triangle we can find V1. Now the first thing we can do is, this is angles on a straight line, so W3 plus this 180 minus 2x must add up to 180 degrees because they are angles on a straight line. And solving for W3, we just take the others to the other side, so 180 minus 180 plus 2x. So this is going to give us, this is going to leave us with 2x. Okay, so this is then 2x. So now to find V1, we just add up all three and equate them to 180. So V1 plus the 2x plus the 90 minus x all adds up to 180 degrees, so that is angles of a triangle. And then to solve for V1 in terms of x, we've got 180 degrees minus 90. This becomes over, it becomes minus 2x, that becomes plus x. And then we've got 180 minus 90 is 90, and minus 2x plus x is minus x. Okay, so here we can see that S2 is equal to angle V1. So therefore angle S2 is equal to angle V1, and therefore we've got that WS is equal to WV. Equal angles, equal sides. Right, then we are done. And that was all of the practice questions, and we are done with this lesson.